Greetings and welcome once again to Shiny Creates Online School. Today, I'll be taking you through KCSE 2025 Chemistry Paper 2. Work with me as I explain all the questions from the first one to the last one in detail. If you are new to this channel, find your time to subscribe to our YouTube channel, Shiny Creates Online School. Welcome. So starting the first question, Table 1 shows part of the periodic table of elements. So we have Table 1 with us here. The table shows part of the periodic table. It has been filled some of the elements among the first 20 elements. Some of them have been filled. So I would like us to start by filling some of the remaining elements that form the first 20 elements in the periodic table before we start answering the questions there down. So from the first 20 elements, from the left corner of the periodic table, we have hydrogen. Then to the right corner of the periodic table, we have helium. Then we have lithium, followed by beryllium, followed by boron, followed by carbon, followed by nitrogen, followed by oxygen, followed by fluorine. Then we have neon. Then we have sodium. And then we have magnesium. We have magnesium, then aluminium, then silicon, phosphorus, sulfur, chlorine, and then we have argon. Then what follows is potassium, and lastly we have calcium as the 20th element in the periodic table. Within this periodic table, we have special elements that are found in between the second and the third group of the periodic table. And in this particular region, we have elements that we call transition elements. These are elements that include, we have iron, we have copper, we have tin, we have gold, we have lead, we have platinum, manganese, zinc, and so forth. These elements are also referred to as D block metals, and they are known to form compounds, colored compounds. And they also have more than 2 oxidation states. Those are elements that we call transition elements. We also have metalloids within the periodic table, and metalloids are those elements that have properties, physical and chemical properties, that are found intermediate between metals and nonmetals. In other words, these are elements that we call semiconductors. They are semi-metals, and some of these metalloids, we have boron, we have silicon, we have germanium, we have arsenic, and so forth, other and more other elements. So, moving to the first question, we are supposed to explain each of the following. The atomic radius of elements decreases from magnesium to chlorine. When you look at the position of magnesium and where the chlorine is, we need to understand that magnesium has 12 protons and chlorine has 17 protons. As we move from magnesium to chlorine, magnesium with 12 and chlorine with 17, we realize that there is an increase in the number of protons as we move across the period where these elements are located. Magnesium with 12 protons, aluminium with 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, and then we have argon 18. As we move across the period 3, we realize that there is increase in the number of protons. And we need to understand that as the number of protons increases, the nuclear attraction also increases, or the effective nuclear charge also increases. And that makes the nucleus to attract more electrons, making the atomic radius to reduce. As the number of protons increases, the effective nuclear charge increases simply because the electrons in the outermost energy level are strongly held by that positive nucleus, and therefore that makes the atom to be reduced in size. So as we move across the period from magnesium to chlorine, there is decrease in the size or the atomic radius, and this is because it is due to increase in effective nuclear charge from magnesium to chlorine. And we have said it's because of the increase in the number of protons from magnesium to chlorine that increases the nuclear attraction, the effective nuclear attraction of those elements. Moving to the next question, Roman 2, the ionization energy of the elements increases from magnesium to chlorine. Remember, learners, ionization energy is the minimum amount of energy required by an element or atom to lose its outermost electron in gaseous form. So, looking at magnesium with 282, aluminium 283, silicon 284, phosphorus 285, sulfur 286, chlorine 287, you realize that the ionization energy of elements will increase from magnesium to chlorine. The energy required to lose electrons, it is easier for magnesium to lose its 2 outermost electrons as compared to aluminium losing its 3 outermost electrons. The energy required to lose 3 electrons in aluminium is more as compared to energy required to lose 2 electrons in magnesium. And why? Why is it that ionization energy of elements increases from magnesium to chlorine? This is because decrease in atomic radius results in increase in the strength of the nuclear force, pulling the outermost electrons towards the nucleus more strongly. It is almost similar to what I've just explained in Roman 1. As the number of protons increases, the nuclear attraction also increases, and therefore we shall require a bit more energy to lose those electrons. And that's the reason we shall require more energy, ionization energy, to lose 7 electrons, outermost electrons in chlorine, than to lose 2 outermost electrons in magnesium. Moving to the next question, B. Explain each of the following in terms of structure and bonding. Explain each of the following in terms of structure and bonding. The melting point of aluminium is higher than that of magnesium. The melting point of aluminium is higher than that of magnesium. Remember, magnesium and aluminium, they are all in the same period. Magnesium with electron arrangement of 282 and aluminium 283. What brings the difference is the number of electrons in the outermost energy level, or what we call the delocalized electrons. So as the number of delocalized electrons increases, the nuclear attraction increases, making the atom to be so small, and the metallic bond in aluminium being stronger than that of magnesium. So the issue of delocalized electrons in aluminium makes the atom to be smaller and increasing the metallic strength, the metallic bond, the metallic bond strength in aluminium as compared to magnesium. So the reason is that aluminium has more delocalized electrons and hence stronger metallic bonds in aluminium. So aluminium has small atomic size and stronger forces of attraction and hence higher melting point in aluminium than in magnesium. Moving to the next question. The melting point of phosphorus is higher than that of chlorine. Looking at the position of phosphorus, phosphorus is position 15 in the periodic table and chlorine is position 17 in the periodic table. Phosphorus, the electronic arrangement is 285 and for chlorine is 287. And we are being asked why melting point of phosphorus is higher than that of chlorine. Remember, phosphorus, when you are writing phosphorus, we do write P4. That is, phosphorus has 4 atoms. It is tetraatomic. But when we are writing chlorine, chlorine is diatomic. And this difference makes the forces, the van der Waals forces of attraction in phosphorus to be a bit more stronger than the ones in chlorine, because chlorine is diatomic and phosphorus is tetraatomic. So the main reason is phosphorus is tetraatomic with larger molecular mass, hence stronger van der Waals forces of attraction than diatomic chlorine. So that is the reason as to why the melting point of phosphorus is higher than that of chlorine. So question number next. Complete table 2 by giving the formula of the oxides of the elements and their acid-base character. So we are given a table here. We have elements. Our elements, we have magnesium, we have aluminium, we have silicon, and we have phosphorus. We are supposed to give the formula of the oxide for each element and indicate whether these elements are acidic or the oxides are acidic, basic, or amphoteric. So we have magnesium. The oxide of magnesium is always MgO, magnesium oxide. Aluminium is aluminium oxide with 2 atoms of aluminium and 3 atoms of oxygen. Silicon, we have SiO3, AO2, silicon with 2 atoms of oxygen. And then we have phosphorus, are 3 oxides. You can also have phosphorus 5 oxide. Looking at the acid-base character, magnesium oxide is always a basic oxide. Aluminium oxide is an amphoteric oxide. It's an amphoteric substance with characters of both acid and base, depending with what it has been reacted with. Silicon 4 oxide is an acidic oxide, and phosphorus 3 oxide is an acidic oxide. Learners, the distribution of the questions of the marks, we had 2 marks in each row. Each have a mark. Same to the second row, each have a mark. Looking at question part D of the question 1, sulfur forms chloride. Sulfur forms chloride, which is sulfur chloride. name the type of bond in the chloride. The type of bond in the chloride, because these are two non-metals that has just formed a bond covalently. So the type of bond in the sulfur chloride is a covalent bond. This is a covalent bond simply because we have two atoms of sulfur and two atoms of chlorine. So the two bonds covalently, so we have two chlorine atoms and two sulfur atoms. Therefore, the type of bond is a covalent bond. Roman 2, determine the oxidation number of sulfur in the chloride. Learners, we have the rules that, or the principles that guide the way we look for oxidation numbers. In this case, we are supposed to determine the oxidation number of sulfur in the chloride. The assumption is the oxidation number of chloride is known, being -1. And as we know, the oxidation number, the oxidation number of atoms in a compound is always equal to 0. And now that we understand and we know the oxidation number of chlorine or chloride is -1, then we can do the substitution and be in a position to obtain the oxidation number of sulfur in the chloride. So we have 2s plus 2 chlorine, and we are using our formula. We have 2 atoms of chlorine of sulfur. That's the reason we are putting 2s plus 2Cl, because we also have 2 atoms of chlorine, and this equals to 0 because this is a neutral compound. And now that we understand the oxidation number of chlorine is -1, so 2s plus 2 into -1 is equals to 0. So we are able to obtain the oxidation number of sulfur as +1. So that's how we determine the oxidation number of sulfur as +1. Question next, silicon tetrachloride fumes in air. Write an equation for the reaction. We need to understand that, learners, when silicon tetrachloride fumes in moist air, it reacts violently with water or water vapor to produce a dense white clouds of solid silicon for oxide. And at the same time, it also leads to formation of a toxic hydrogen chloride gas. So in this case, when shall be writing a reaction, an equation between a silicon tetrachloride and water or water vapor. In this case, we are going to obtain silicon oxide, which is a solid, and hydrogen chloride gas, which is a toxic gas that we are talking about. So we have silicon chloride, tetrachloride, or silicon tetrachloride, plus 2 molecules of water. We obtain silicon oxide, which is a solid, plus hydrogen chloride gas 4 molecules. And this is the gas that we are saying is very toxic. So this is a well-balanced equation for the same. Moving to the next question. Silicon is a metalloid. What is meant by the term metalloid? I defined this before. Metalloids are elements that possess both metallic and metallic properties, or in other words, we say they are elements which have properties intermediate between metals and non-metals. Some of these metals or elements, we have boron, we have silicon, we have arsenic, we have germanium, we have tellurium, and we also have polonium as some of the examples of the metalloids. And lastly, in this question, state one use of silicon as a metalloid. Metalloids, the elements that are commonly used in many applications. Some of the applications we have, it's used as transistors. They're also used to make computer chips, and metalloids can also be used to make solar cells. They can also be used to make alloys because they do improve our strength of a particular metal. So those are some of the uses of metalloids. Question 2. State the names of the following compounds. Roman 1. We have a compound with CH3, CH2 in bracket 5, and CH3. So when you're given this kind of a question, you can have a rough work somewhere where you can have the illustration of the same. So in this case, I'm going to have 7 carbons. I'm going to have 7 carbons. 1, 2, 3, 4, 5, 6, 7. And the first carbon carries 3 hydrogens. So I insert the hydrogens. Then we have other 5 carbons, each carrying 2 hydrogens. Each carrying 2 hydrogens. Then the last carbon carries 3 hydrogens from what we have in our compound. So looking at this compound, we can notice that the carbons, they are bonded by a single bond, and this classifies it as an alkane. And because it has a maximum of 7, it has 7 carbons. We have 1, 2, 3, 4, 5, 6, 7 carbons, and hydrogens. This is an alkane, and the alkane with 7 carbons is always what we call an heptane. This is what we call an heptane. So the correct answer to our question 2A Roman 1 is heptane. Then moving to the next part of this question, we have carbon CH3, carbon CH2, 3 of them. Then we have carbon, a triple bond, and carbon and hydrogen. So in this case, I can still have a summary whereby I can open it up and be in a position to name it. So In this case, I will have the first carbon 1, the second carbon, which are 3, 1, 2, 3, and then another carbon, then a triple bond, a carbon. So the first carbon carries 3 hydrogens. The other 3 carbons carries 2 hydrogens each. The other carbon, as you can all see, it's a stable carbon with 4 bonds. Remember, a carbon atom is always surrounded by 4 bonds, so we have already 3 plus 1. Those are 4. And then the last carbon is surrounded by 1 hydrogen. And the presence of triple bond classifies this compound as an alkyne. So, from what we are given, the triple bond is located in the first carbon in this compound. Therefore, learners, our compound is, because you have seen, it has 6 carbons. It is an X1 ion. X1 ion, that's the correct answer to that question. Moving to the next question. Part B of this question. Figure 1 shows extraction of copper from copper pyrites. CuFeS2, that's the formula of copper pyrites, the chief ore of copper metal. We also have other ores where copper can be extracted. We have malachite. Malachite is a basic copper carbonate. We also have chalcocite, which is copper 1 sulfide. We also have atacamite, which is basic copper chloride, as another ore to copper metal. So looking at this particular setup, we need to understand that the extraction of copper consists of several steps. And the first step, the steps are always 3 main steps. The first step is, or stage, we always start with the concentration of the ore. After we concentrate the ore, we always roast the ore in a furnace. After roasting the ore, we later refine the ore and make it pure, because whatever is formed after roasting is always brittle copper, which is not pure copper. So copper is passed, the chief ore of copper is passed through those stages to ensure that we obtain a pure copper. So the concentration of the ore is done by flotation. We understand that. And then later we roast it, and then we refine it at the end. So we need to understand that the process starts of roasting the ore starts with the chief ore being roasted in air in a furnace, and we roast the ore, which is copper pyrite, by reacting it with oxygen, whereby we form copper 1 sulfide, iron 2 oxide, and we're able to release a gas which is sulfur 4 oxide gas. So whatever is taking place in chamber 1, we are roasting copper pyrites, whereby we are reacting with it with oxygen in this air, and we're able to form copper 1 sulfide and copper 2 oxide, and at the same time we release sulfur 4 oxide gas, which is released and can be subjected to another industrial process, the contact process in the manufacture of sulfuric acid. Once that is done, to separate the copper 1 sulfide from the iron 2 oxide, silicon 4 oxide, or what we call silica. Silica is always added to the mixture, which is heated to about 1000 degrees Celsius, and copper 1 sulfide is able now to melt. Copper 1 sulfide is able to melt, and it falls into the bottom part of the furnace as iron 2 oxide reacts with silica to form what we call a slag, and this slag is iron silicate, iron 2 silicate, and that's the slag that we are talking about. So we can see the reaction that takes place in chamber 1, which leads to formation of copper 1 sulfide, iron 2 oxide, and the release of gas C, which is sulfur 4 oxide gas. And I've said that the copper 1 sulfide and iron oxide mixture, once they are formed, we add substance B, and our substance B is silicate or silicon 4 oxide, which is heated in chamber 2. Copper 1 oxide sulfide melts, and the iron 2 oxide reacts with silica to form iron 2 silicate, which is collected at a bottom part of the furnace as a slag. And then after that, what follows once we form, so we have started sulfur 4 oxide, and then the reaction that takes place in the chamber 2 is silicon 4 oxide reacting with oxygen, iron 2 oxide. Remember, copper 1 sulfide does not react, it just melts and it moves to the next chamber. So once we have formed that, our slag is iron 2 silicate. Then in chamber 3, the copper 1 sulfide is taken in another converter with controlled amount or supply of oxygen, where part of copper 1 sulfide is converted to copper 1 oxide. And then what follows is the copper 1 oxide formed reacting with the remaining part of copper 1 sulfide to form liquid or molten copper, and we're able to release again gas C, which is sulfur 4 oxide gas. So looking at that breakdown, we're able to answer the questions that follows. We are being taught to identify gas C. Gas C, in this case, we can see it at this point and also at this point. So gas C is sulfur 4 oxide. So gas C is sulfur 4 oxide. Write an equation for the reaction that takes place in chamber 1. The reaction that takes place in chamber 1, we have said that is the copper pyrite or the chief ore reacting with oxygen to form copper 1 sulfide, iron 2 oxide, and a release of sulfur 4 oxide gas. So the equation is as follows. Balanced equation. Please don't forget to include the state symbols. This is a solid, this is a gas, oxygen is a gas. Then copper 2 sulfide is again copper, it's again a solid, and then we have Iron 2 oxide is again a solid, and then we have gas, sulfur 4 oxide gas. So please don't forget to include the state samples of these products and reactants. Then the next question is you identify substance B. Substance B, we had already identified it. Substance B, it's silicon 4 oxide, which we were calling silica. Then we have substance, we give the formula of the main compound in the slug. We have said that the main compound in the slug, we have said that silica reacts with iron 2 oxide to form iron 2 silicate. So the formula is FeSiO3. In this case, learners, you are supposed only to give a formula. You are only supposed to give a formula but not the name. So what was being marked is a correct formula. So part E of this question, write equations for the reaction that takes place in chamber 3. Learners, in chamber 3, that's where we add copper 1 sulfide being reacted with controlled amount of oxygen, leading to formation of copper 1 oxide and sulfur 4 oxide gas in the first step. And in the next step, we add the copper 1 oxide formed reacting with the remaining copper 1 sulfide, leading to formation of copper metal and sulfur 4 oxide gas again, which is our gas C. Please, learners, don't forget to include the state samples in these particular compounds and reactants and products. Oxygen is a gas, sulfur, copper 2 oxide, copper 2 oxide, copper 1 oxide is a solid, copper 1 sulfide is a solid. Copper, in this case, is formed in form of a liquid, some molten state. So please don't forget to insert the state samples of these substances for whenever the equation is being marked. An equation is always correct when the state samples are correctly written, and again, the equation is balanced. So please include the state samples. Don't fully use what I've just indicated in this question. Moving to the next question, part F. Describe the process that is used to purify the impure copper. What we need to understand, learners, is that the copper that is always formed is always impure copper. We actually call it brittle copper, and this is because as it tries to solidify, the bubbles of sulfur 4 oxide gas released makes it to have or to appear blistered or to have a blistered appearance, and that's the reason we call it a blister copper. It is not fully pure copper, so we always purify this particular copper using electrolytic method, where we place the pure copper on the cathode and an impure copper on the anode, and then we connect or we insert it or we dip it in a solution of copper sulfate. Then we allow electric current to pass through them, and then from there we're able to collect a pure copper which deposits on the cathode side of the electrochemical cell. And then we're able to collect impurities that we call sludge, which includes traces of gold, silver, and platinum at the bottom of the electrolytic cell. So this is how we purify impure copper. Electronic refining method is used when impure copper is placed at the anode and a pure copper is placed at the cathode, and both are dipped in copper sulfate solution. During electrolysis, copper dissociates at the anode and then gets deposited as pure copper at the cathode. So that's the method that we use, and in this case, we don't use inert electrodes, we just use pure copper and impure copper, and we all insert them in a solution of copper sulfate. So that's how we refine or we purify the impure copper. Moving to the next question. When left exposed for a long time in air, copper coins, they turn green. Explain this observation. So whenever you expose copper, remember in air we have oxygen, we also have carbon dioxide. So what happens? We have the carbon dioxide. So carbon dioxide, water and oxygen in air, they react with copper, leading to formation of green layer of copper 2 carbonate, and that's what makes copper to turn to green, because copper 2 carbonate is green in color. So that was the correct answer to that question. And then we have the next question, number 3, part A. State what is meant by standard enthalpy of formation of a compound. So the standard enthalpy of formation, we need to understand that whenever we are forming a compound, we need some elements that come together to form that compound. So the energy that is required to form that compound is what we call the enthalpy of formation of a compound. So the enthalpy of formation of a compound is the energy change that occurs, in this case, when one mole of a substance is formed from its constituent elements at standard conditions. So that's what we call the standard enthalpy of formation. Standard, we need 1 mole of that substance to be formed. Part B of this question, number 3. Table 3 gives enthalpy of formation of some compounds. So we have table 3, we have compound, and we have the standard enthalpy of formation given in kilojoules per mole. We have the compound carbon dioxide, its enthalpy, the standard enthalpy of formation being negative 393 kilojoules per mole. Then we have water, its standard enthalpy of formation being negative 286 kilojoules per mole. Then we have propane, its enthalpy of formation, standard enthalpy of formation is negative 104 kilojoules per mole. And then we have questions. Write the thermochemical equation for the formation of carbon dioxide. So for the formation of carbon dioxide, we need to understand, learners, that for us to form carbon dioxide, because we have defined the standard enthalpy of formation as the enthalpy change that occurs when 1 mole of a substance, kindly take note of that, is formed from its constituent elements at standard conditions. So in this case, we need to look for the elements that lead to formation of carbon dioxide. So in this case, the elements that forms carbon dioxide is carbon and oxygen, and the product must be 1 mole. So I need carbon plus oxygen that will lead to formation of 1 mole of carbon dioxide. So in this case, carbon, which is a solid, plus oxygen, which is a gas, which leads to formation of carbon dioxide gas, and the equation is balanced. And for a complete thermochemical equation, we must write the enthalpy change at the end of that equation. So we have carbon, solid, oxygen gas, leading to formation of 1 mole of carbon. So you can see that this, whatever is being formed, is 1 mole. I've not balanced with anything here, so it remains to be 1 mole. So the enthalpy change is negative. There's a negative here, negative 393 kilojoules per mole. So that is the correct thermochemical equation for the formation of carbon for oxide. Then we have water. For us to form water, we need hydrogen gas and oxygen gas that must lead to formation of 1 mole of water. So in this case, we have hydrogen, one hydrogen molecule, then oxygen, because in this case we must maintain the 1 mole of water here. We have to balance the oxygen with half to ensure that we have 1 mole, 1 atom of oxygen, like on our product side. So we are trying to maintain the 1 mole of the product or the compound being formed, because in the enthalpy of formation we must lead formation of 1 mole of the substance. So in this case we have the enthalpy still being written at the end of the equation. So in this case we also have to include the state simples of these particular substances. For the equation will be marked plus the state simples. So those were the thermochemical equations that we are supposed to write in Roman 1. Moving to the next question, study the energy level diagram in figure 2 and answer the questions using the data in table 3. When you look at this that we call energy level diagram, you notice that we have the arrows moving down, and this indicates that the type of reaction in this case is exothermic, and we can see that we have negatives here indicating that the reactions are exothermic. So in our case here, we need to understand that we have formation of propane. So we have the enthalpy of formation propane. Then from propane, we move to carbon dioxide and water. So we have the enthalpy of combustion. Anytime we do combustion of an organic compound, we lead to formation of carbon dioxide and water. So we need to understand that propane here is being combusted to form carbon dioxide and water. In the first case, we add the atoms that lead to formation of propane. So this is the enthalpy of formation propane. So enthalpy change H1, that is the enthalpy of formation propane. We need to understand that this is the enthalpy of formation propane, and this is the enthalpy change of combustion. This is the enthalpy change of combustion propane. And then on the other side, we have carbon, hydrogen that leads to formation of carbon dioxide and water. In this case, we are carrying combustion of carbon and hydrogen. In this case, it's only that one arrow has been used. So this is the enthalpy of combustion. We have carbon, and we also have the enthalpy of combustion hydrogen. So we need to understand the energy level diagram very well before we start looking at it. So in our case here, we are supposed to give the value of enthalpy change H1. Enthalpy change H1, we are only supposed to read from what we have, because you understand this is the enthalpy of formation propane, and from our table here we have our enthalpy of formation propane being negative 104 kilojoules per mole. So the correct answer is negative 104 kilojoules per mole. So Roman 2 of this question, we need to calculate the values of enthalpy change to H2 and enthalpy change H3. We need to understand that enthalpy change H2, it was the enthalpies of combustion, carbon and hydrogen. and H3 was the enthalpy of combustion propane. So in this case, we can come up with what we call the energy cycle diagram that follows the S law, that the energy change in converting products to reactants, reactants to products is the same regardless the route that is being followed. So in this case, I'll use the energy level diagram to come up with an energy cycle diagram. So in this case, I will start with the formation of propane cells. So I have a carbon hydrogen that will lead to formation of propane. That is the enthalpy of formation propane, which I indicated it as enthalpy change A. And then I also have the enthalpies of combustion, carbon and hydrogen, that leads to formation of water. And still on the other side, I have the enthalpy of combustion. I have the enthalpies of combustion propane self that leads to formation of carbon dioxide and water. So in this case, I can still use this route and I'll get the enthalpy change. And I use these two routes and I get the same change in energy. So this is what we call the S law. That's application of the S law. Whenever I use this route and this route, this route, this route, and this route, the enthalpy change will be the same. So in this case, I'm trying to ask myself, how do I determine the enthalpy change? The enthalpy change B. Enthalpy change B is our enthalpy change H3, and then we have enthalpy change H2, which is C and B. So from the table, we are already given the enthalpy changes C and B, but for 1 mole of those substances. So in this case, I'm supposed to look for enthalpy change H2. How do I look for enthalpy change H2? So we understand that A plus B is same as C plus D. So how do I get that? I have H2 being, how do I get H2? H2 will just be and that C plus B. So in this case, I was given the enthalpy of combustion carbon, which was 1 carbon, but now in this case I have 3 moles of carbon. So I'll be taking the enthalpy change which I was given per mole, negative 393, but I multiply by 3 because the atoms were 3. And for hydrogen combustion, I'll be taking 4 because there are 4 atoms or moles, and I multiply by negative 286, and through that I'll be able to get the enthalpy change H2. So the correct answer to this question is negative 2323 kilojoules per mole. Then to determine H3, I need to apply the formula that A plus B is equals to C plus D. And because I have A plus B, and I also have A, I don't have B, I have C and D. So in this case, I have C and D, I have A, I don't have B. So A is negative 104 plus B, which I don't have, is equals to 3 for combustion carbon and 4 for combustion nitrogen. So in this case, when I work out, I'll be able to get B as negative 2219 kilojoules per mole. So in this case, my H3 is negative 2219 kilojoules per mole as my H3. Moving to the next question. When a sample of butane, C4H10, was burnt, the heat produced raised the temperature of 500 grams of water by 35 degrees Celsius. So the temperature rise was 35 degrees Celsius. The specific heat capacity of water is 4.2 joules per gram per Kelvin, and we are supposed to calculate the heat change for the reaction. The heat change for the reaction is determined by taking the MC delta T, which is the mass of the solution, multiplied by the specific heat capacity, and then we multiply by the heat change. In this case, we have 500, and because 500 is in grams, the mass of water, I divide by 1,000 to convert it to kilograms, and then I multiply by the temperature rise, which is change, which is 35 degrees Celsius, and in this case, it is 35 Kelvin. We just do automatic conversion, 35 Kelvin, and then I multiply by 4.2, in this case, kilojoules per kilogram per Kelvin, and I'll be able to get the energy change as 73.5 kilojoules. In this case, I can still include the negative to show that it was exothermic because it was a temperature rise. So it can still be negative 73.5 kilojoules, not per mole in this case, but just kilojoules. So we were supposed to determine the heat change for the reaction. That was the heat change for the reaction. In Roman 2 of the same question, the mass, we calculate the mass of butane that was burnt, given that the heat of combustion of 1 mole of butane is negative 2880 kilojoules per mole. So in this case, we have to start by looking at the number of moles in the number of energy that we have already determined. And now that we have 1 mole for this one, so 1 mole is in 2880. What about our 73.5 kilojoules per mole? And you're able to get our moles as 0.0255 moles. So with this, and we have the molar mass, our molar mass of butane, now butane is C4HR10, which gives us 58 as our molar mass, which is still equal to 1 mole. So using the moles that we determined in the energy that we have obtained, we multiply the molar mass by the number of moles, and you're able to get the mass as 1.479 grams. So the mass of butane that was obtained is 1.479 grams. Question number 4. Describe how a sample of chlorine gas can be prepared using the following compounds. We have solid sodium chloride, which can be rock salt, solid manganese oxide, and concentrated sulfuric 6 acid. You need to understand that in Form 3, you are taken through how chlorine gas is prepared, and chlorine gas is prepared through oxidation of hydrogen chloride with a strong oxidizing agent. In this case, we can have potassium manganate 7. You can still use hydrogen peroxide. You can still use manganese oxide, whereby we just drop it directly using a dropping funnel or filter funnel into the solids that they act as oxidizing agents. But in this case, the question is a bit indirect. We are supposed to pass through some steps until we obtain the hydrogen chloride gas, or what we call the hydrochloric acid that we actually use. So in this case, we have 3 materials. We have solid sodium chloride, and we have a sulfuric 6 acid concentrated. So in this case, we must start by reacting the sodium chloride and sulfuric 6 acid. Remember, sulfuric 6 acid is less volatile and it's able to displace any salt of any other acid or mineral acid. So in this case, sodium chloride reacted with sulfuric 6 acid, which shall be able to obtain hydrogen chloride gas, because sulfuric is less volatile, so it is able to displace sodium from sodium chloride. and then from there we shall be able to react it with manganese oxide to obtain our chlorine gas. So in this case, what we do, we add concentrated sulfuric 6 acid to sodium chloride in a conical flask. So I've started by taking sulfuric 6 acid and add to sodium chloride in a conical flask, and then I'll be able to collect hydrogen chloride gas. Then the hydrogen chloride gas produced shall be collected using the downward delivery, and then from there we add solid manganese oxide, which is our oxidizing agent, to the produced gas to produce chlorine gas, and then it's collected by downward delivery. So in this case, we shall oxidize our HCl gas using manganese oxide to obtain chlorine gas. Moving to the next question, figure 3 is a flowchart showing some reactions of chlorine. So we need to understand that we have several reactions of chlorine under the topic chlorine and its compound, the chemical properties of chlorine. So we need to understand that chlorine, we have chlorine reacting with water, we have chlorine reacting with metals, and we still have chlorine reacting with non-metals like phosphorus, and we also have chlorine reacting with alkalis. So we have chlorine reacting with hot and cold alkalis. So in this case, we have chlorine at this point. We're starting with chlorine at this point, chlorine gas, and then we move to step 1. Chlorine is being reacted with iron. So chlorine being reacted with iron will lead to formation of iron 3 chloride. Then moving to step 2, chlorine is being reacted with something in step 2 and leads to formation of sodium chlorate 5, and then we move to chlorine gas being reacted with phosphorus, and it leads to formation of two products, D and E. So in this case, when chlorine reacts with phosphorus, we need to understand that chlorine reacts with phosphorus to form a mixture of a white solid, a mixture of phosphorus 3 chloride and phosphorus 5 chloride, and therefore D will be phosphorus 3 chloride and E will be phosphorus 5 chloride. The 3 will come first and then the 5 come last. And that's the reason I have D as my phosphorus 3 chloride and E phosphorus 5 chloride. So we are supposed to give the name of the compound C, and we have seen that compound D, chlorine reacting with metals, we form the chlorides of that metal. So in this case, you're forming chloride, iron 3 chloride, not 2, iron 3 chloride, which is compound C in step 1. So the correct answer is iron 3 chloride. We are supposed to name the compound, not to give the formula. Then we have from and 2, state the reagent and conditions necessary for the reaction in step 2. In step 2, we need to understand that this is the property of chlorine which reacts with hot and cold alkalis like sodium hydroxide, cold and warm and hot. In this case, we are not forming chloric 1 or sodium chloride 1. We are not forming chloride 1, but we are forming chloride 5. And in this case, we form chloride 1 when the alkali is hot. So the reagent in this case is sodium hydroxide, which is concentrated sodium hydroxide, and the condition that we require in this case is always heat, because it must be hot for the reaction to lead to the formation of sodium chlorate 5. So the condition in this case is high temperature, so it's heat. Then Roman 3, two compounds are formed in the reaction in step 3. Give the formula of each of the two compounds. So in this case, I've said that D shall be phosphorus 3 chloride and E shall be phosphorus 5 chloride. Remember, I said when phosphorus react with chlorine, it leads to formation of a mixture of two chlorides, phosphorus 3 chloride and phosphorus 5 chloride. And the reason as to why I've made D to be 3 or phosphorus 3 chloride and E to be phosphorus 5 chloride because the smaller chloride, the one with less number of atoms will comes first, and then the other one comes later. So we have D coming first than E. So phosphorus 3 chloride and phosphorus 5 chloride are the correct answers to Roman number 3. We have part C of this question. Write an equation for the reaction that takes place when chlorine gas reacts with aqueous hydrogen sulfide. When chlorine gas reacts with aqueous hydrogen sulfide, it's another property of chlorine, and when chlorine gas is reacted with aqueous hydrogen sulfide, there's a kind of redox reaction that takes place, whereby hydrogen sulfide acts as a strong reducing agent, and the chlorine gas acts as a strong oxidizing agent. So what happens? The hydrogen sulfide is always oxidized to sulfur, which is a yellow solid, and the chlorine is reduced to a colorless gas, hydrogen chloride gas. So in this case, our formula is hydrogen sulfide, again indicate the state samples plus chlorine. We obtain sulfur, which is a yellow solid, plus hydrogen chloride gas, in this case a gas. So the equation should be balanced by putting a 2 in the hydrogen chloride. So we put a 2 in hydrogen chloride, and through that we shall have balanced the equation. Roman D, you state the observation made when chlorine gas is bubbled into aqueous potassium iodide. So this is the issue of the single displacement. In this case, chlorine is a more reactive gas compared to iodine. So there will be single displacement, whereby we shall be able to form potassium chloride, and we shall be able to deposit a solid of iodine in the container where the reaction is taking place. Or we may be able to see a brown substance depositing. So in this case, we may be able to see color solution changing to dark brown, chlorine gas. So in this case, potassium iodide is colorless. After displacement, iodine molecules are always brown in solution. So we shall be able to see colorless solution changing to dark brown. We may also be in a position to see a black solid depositing in the container. So that is the observation done, because chlorine is able to displace iodine from its salt. So that is what actually takes place. Then we have moist red litmus paper is placed in a gas jar of chlorine gas. A red litmus paper in chlorine is always bleached, or it changes to whitish in color. So in this case, moist red litmus change or turns to white, or it gets bleached in that case. So we have part E of this question. Write an ionic equation for the reaction that takes place when aqueous lead 2 nitrate is added to aqueous potassium chloride. So we need to have the knowledge of the soluble or salt, the solubility of different types of salts, in this case, we need to understand that aqueous lead 2 nitrate reacting with potassium chloride, there will be precipitation taking place there. Noting that lead chloride is always insoluble, therefore it will lead to formation of a precipitate. So in this case, there will be an ion-cation exchange where lead picks the chloride and the potassium picks the nitrate in lead. Therefore, we shall have a mixture of two salts, one soluble, another one insoluble. So the ionic equation that leads to the formation of the precipitate comes from lead ions reacting with the chloride ions, and then leads to formation of lead chloride, which is always a precipitate or a solid. So in this case, we have lead 2 ions, which is aqueous. Please, learners, don't forget to put or indicate that the state symbols aqueous for lead 2 ions, plus the 2 chloride ions still aqueous, and then we are able to obtain lead 2 chloride, which is a solid. In this case, please indicate S to show that this is a solid or a precipitate, and that is the ionic equation that we are talking about. Look at the equation, is still balanced. Part F of this question, you state the reason. State the reason by chloride is used. Why chloride in this case is why chloride or chlorine is used in water treatment. So chlorine in water leads to formation of chloric 1 acid. Chloric 1 acid leads to kill, or it leads to it kills the microorganisms through oxidation. So we say the correct answer is the chlorine reacts with water to form chloric 1 acid that kills the germs through oxidation. That's the correct answer to this question. Question number 5. Figure 5 shows the down cell used in the extraction of sodium from molten sodium chloride. This is the down cell that is used in the extraction of sodium metal from rock salt, which is molten in molten state. And when you look at the down cell, we can see on this inlet we have sodium chloride that is that enters through this particular inlet. Then we have chlorine gas coming out from this other outlet, and an outlet here where sodium metal in form of a liquid or molten state is released from the cell. So as we know, learners, sodium is extracted from its chief oil, rock salt, sodium chloride, which is melted or is molten and put in the down cell using the Downs process. And the down cell consists of several parts, whereby we have a brick coated tank, and then we have the electrodes, and we also have a steel gauge diaphragm. So we have electrode A. Electrode A, this are what we call the steel cathode. We also have it on the other right hand side, and then we have electrode B, which is always used as the carbon anode. So what happens once we put this the sodium chloride is put in the down cell? Electrolysis method is used where chloride ions are discharged at the anode, that is electrode B. After they are discharged at electrode B, they lose electrons and chlorine gas is released. That is at the anode. At the cathode, sodium ions are discharged. They gain electrons, and sodium metal in form of a liquid is formed at electrodes A. And we can see a steel gauge, a diaphragm, which separates the chlorine formed from the sodium formed and prevents them from recombining once more. So that's the work of the steel gauge diaphragm. So looking at the questions, identify the anode and cathode in the cell, and you give a result. The anode, as I've said, is electrode B, and electrode, the reason as to why we are saying is electrode B is because the chlorine is produced at the anode where oxidation takes place. So chlorine that you can see here can only be produced at the anode after oxidation takes place. Then we have cathode. Our cathode we have said is electrodes A. The reason we are saying A is our cathode is because in the down cell sodium is produced at the cathode. At the cathode, that is where reduction takes place. Then we have Roman 2. State the purpose of the steel gauge diaphragm. As I've said, the work of the steel gauge is to prevent chlorine and sodium from recombining. So once we form chlorine at the anode and the sodium at the cathode, there are chances of them recombining, and that's the reason we steel gauge is placed in between them so that the two do not recombine. Part B of the question. Table 4 shows the melting point and boiling point of sodium and sodium chloride. So we have table 4 at this point. We have the substance and we have the melting point in degrees Celsius, and we also have the boiling point also given in degrees Celsius. Sodium, the melting point is 97.8. Its boiling point is given as 890 degrees Celsius. Sodium chloride 801, the melting point, and the boiling point 1467 degrees Celsius. So given that the down cell is operated at 600 degrees Celsius, state how this temperature is achieved. So when you look at the boiling point, the melting point of sodium chloride is above the operation or the operational temperature, which is 600 degrees Celsius, and even the boiling points of sodium and sodium chloride are also above the operational temperature during the extraction of sodium metal. So how do we achieve this temperature? As we understand the process of extracting sodium, we have sodium chloride, we have calcium chloride, which is added to ensure the temperature is lowered to make the process a bit more economical or a bit more cheaper, because the process uses electricity and that may be very much expensive, and that's the reason we have to add calcium chloride to lower the melting point or these high temperatures to around 600 degrees Celsius. So in this case, calcium chloride is added to lower the melting point from 801 degrees Celsius to 600 degrees Celsius. State the advantage of operating at 600 degrees Celsius. We have said that the process is economical, it's a bit less expensive, or it is cheap. So we say it lowers the cost of production since it is economical. So very little electricity is used, and this makes the process a bit more cheaper or makes it a bit economical. Then we have from 1-3, state the physical state in which sodium is obtained from the cell, giving a reason. So we have sodium is extracted or is obtained in form of a molten or in molten state or in a liquid. And the reason is because the operating temperature is always above the melting point of sodium. So if it's the operating temperature is above the melting point, automatically the state of the product or the method being extracted will be in liquid form because it will have melted and become a liquid. Part C of the question, starting with 1,000 kilograms of sodium chloride, calculate the mass of sodium produced. So we have 1,000 kilograms of sodium chloride. So we have to calculate the mass of sodium that was produced. Within that sodium chloride, using 1,000 kilograms of sodium chloride, we calculate the mass of sodium produced. So what you need to do, we need to determine the mass, the molar mass of sodium chloride, which is 58.5. And from there, we take the mass of sodium produced using the total amount of mass in sodium chloride. So we take the mass of sodium, which is always 23. So it is 23 of the total amount or the total mass of sodium chloride is 58.5. Then we multiply by the 1,000, which is the total mass of sodium chloride, and we're able to get the mass of sodium formed or produced when 1,000 kilograms of sodium chloride is used. So this is the mass of sodium produced, 393.162 kilograms. Part D of the question, explain how a sample of solid sodium should be stored in the laboratory. As you understand, sodium is one of the most reactive metals that is used in the school laboratories and a well-known metal that is very much reactive to oxygen or air and water. So a special method for storage is used to keep or to store sodium metal to prevent it from reacting with moisture and air. So what is done? Sodium is stored in enclosed containers containing paraffin to prevent it from reacting with those substances, that is air and moisture. So we've said that it's stored under paraffin or oil to prevent it from reacting with both atmospheric oxygen and moisture or water. Moving to the next question, state one industrial use of sodium. Sodium has several uses. We have making of sodium vapor, which is used in lamps, sodium lamps. We also have in manufacturing of sodium peroxide and other more uses of sodium. Question number 6. The products of electrolysis depends on the condition used. Part A, Roman 1, state the conditions if the products of electrolysis of aqueous copper 2 sulfate are oxygen and copper. So what is the condition when we are electrolyzing aqueous copper 2 sulfate and we end up obtaining oxygen at the anode and copper at the cathode? So the condition that is followed in that case is use of inert electrode. when you use an inert electrode, for instance, graphite, you notice that at the anode, instead of forming or discharging copper, we end up obtaining oxygen, and at the cathode we obtain copper. So in the factor that is being utilized here is using inert electrode, for instance, graphite. What about a case where in both cathode and anode we end up obtaining copper? This is when we use copper electrodes both at the anode and at the cathode. So those are the factors that are being considered. Use of active electrodes, that is copper electrode, both at the cathode and the anode. Moving to the next question, Roman 2. During electrolysis of an electrolyte containing aqueous A ions, the charge of 3, 19.4 grams of A were obtained when a current of 15 amperes was passed through it for 2 hours. Write the Arv equation for the reaction that took place. This is a reaction that takes place at the cathode of the cell. And what happens is that the ions of A gains electrons and we're able to obtain a solid, or there will be deposition of a solid of A at the cathode. So in this case, we have A3 power 3, that is A ions, a charge of 3 positive, plus 3 electrons, we're able to obtain a solid. So in this case, students, kindly don't forget to include the state simples. We have the ions. In this case, they are aqueous form, and then the A will be in solid form. Please don't forget to include that whenever you are answering this kind of a question. So this was supposed to give you 1 mark after including the state simples. Roman 2, determine the relative atomic mass of A. How do we determine the relative atomic mass of A? We already have the mass that was formed or that was deposited at the cathode. So learners, we need to understand that we are given the number of Faradays, or the 1 Faraday as 96,500 coulombs. So we need first to determine the amount of electricity that was used or that was passed. And how do we determine the amount of electricity? And learners, we need to understand this formula, that whenever you are given this kind of a question and you need to determine mass deposited, always use this formula, that mass is given by Q multiplied by RAM divided by C multiplied by F. In our case, C is the charge for that metal that is being reduced, and F is 1 Faraday. So in my case, I have to look or determine Q, and in my Q is given by IT. I is the current and T is time in seconds. So my I is 15 amperes and T in seconds. I take 2 hours multiplied by 60 to change the time into seconds. So I'll be able to get the time in seconds. So in this case, I take 2 times 60, that is 120, and then I multiply by 60. I multiply by 60. What do I get? Is 2 times 60 times 60. It is equivalent to 7,200 or 7,200. Take note of that. And then once I get 7,200, I'll now be able to, I don't have the RAM. Take note of that. The C is 3 because it is 3 positive, and F is 96,500. So I'm going to take the IT, that is, I take 15 multiply by 7,200. I take 15 multiply by 7,200, and that's when I'll get 108,000 coulombs. So that is the electricity, the amount of electricity that I'm going to obtain. So once I have all that, I'll be able to substitute to my equation. When I substitute here, I'll be able to work it out, and the unknown in this case is the RAM. So using my mass is equals to 1,008,000 multiplied by RAM over 3 times 96,500, I'll be able to get 52. And 52 is the RAM of that particular method. So learners, the reason as to why I'm saying that it's good to always have this formula in your mind, assuming that in one point you are supposed to look for the charge of that particular method. So you just do your substitution, and at the end, you'll be able to get the charge. In any case, you are supposed to look for the time. Again, you'll still be in a position to get the time. Learners, this was method 1. We also have an alternative method in case where you don't have the formula in your mind. So what we do, we determine the amount of electricity in 1 mole of A, and in 1 mole of A, because we discharge 3 ions, we take the 96,500, that is 1 Faraday. So in this case, we have 3 Faradays. We multiply by 3, we get 2,089,500 coulombs. And then we determine the number of moles in the amount of electricity that we had already obtained, which is 1,008,000. So we need to understand that in 1 mole of electricity, we have 289,500 coulombs. So we determine the amount of electricity in 108,000. So we determine the amount of electricity in 108,000, and we're able to get now the moles there. Once we get the moles, we already have the mass that was deposited. So if we have the moles, these moles will be equivalent to the mass that were deposited. So we need only to apply the first principle approach and ask ourselves if this mass is equivalent to these moles. What about 1 mole? Because you understand that relative atomic mass is always equivalent to 1 mole. So we ask ourselves, what about 1 mole? And again, we are going to get our RAM as 52. So let's take note of that. So part B of question 6. Study the following cell representation diagram and answer the questions that follow. We have a representation or a cell notation with us here, whereby we have a nickel cell, half cell, combined with a silver cell, and we have the overall EMF or electrode potential as positive 1.05 volts. And we are in Roman 1, we are supposed to state this what the simple these two lines represent in the diagram. So what does these two lines represent, learners? The two lines in a cell notation represents a salt bridge which connects the two R cells and ensures that there is balance of ions during the flow of electrons. So we call it a salt bridge. Write an equation for the reaction that occurs in the cell. So we are supposed to write an overall equation. In this case, we can see that nickel is being oxidized and silver is being reduced. So we are going to start with nickel as a metal and silver plus a silver in ion form, and we're able to obtain nickel in form of ions, aqueous, and silver as a solid, and from there we write the cell EMF. So we have our equation here, nickel solid. Please learners, don't forget to write the state symbols. Nickel solid S plus 2 silver ions, aqueous, and we're able to obtain silver ions, that is nickel ions in aqueous form, plus silver solid. So this shows that nickel has been oxidized. Nickel has been oxidized. You can see from nickel, the oxidation number is 0 at this point, and it moves to positive 3. From silver, it is positive 1, it moves to 0. So there is a redox reaction taking place here, and we can see that. So once we have done that, learners, we also supposed to write this EMF at this point at the end. So that was our equation for the cell, not forgetting to write the state symbols of these substances. Question number next. Given that the E naught value of silver R cell is positive 0.80 volts, you calculate the E naught value of nickel. So we already have the overall EMF value or electrode potential, and we are already given the one for silver. So how do we determine the one for nickel? So we need to understand that EMF of a cell is given by E reduction minus E oxidation. E is the E naught of a cell that is being reduced. So the cell that is being reduced in our case is silver. Silver is being reduced, and we have nickel being oxidized. So we are going to take the overall EMF value, which is positive 1.05 volts, is equals to E being reduced is positive 0.80 volts minus the E naught value of nickel, and we're able to obtain the E naught value of nickel as, when you take, in this case, I'm going to have to take the positive 1.05 to this side and the nickel to the other side, and I'm going to have a negative 0.25 volts for nickel half cell. So that is the correct answer. Moving to the next question. State how the EMF of a cell can be used to predict whether a reaction is feasible. So how do we do this? We always use the formula EMF is equals to E reduction minus E oxidation. And once I do that, if the overall EMF is positive, then the reaction is visible. So that is how we do it. Using the formula E reduction minus E oxidation, if the overall EMF is positive, then the reaction is visible. Moving to the next question. Corrosion of a metal involves formation of an oxide layer on the metal surface. Explain why corrosion of aluminium is protective while that of iron is destructive. Remember, aluminium forms an oxide, aluminium oxide, which does not wear out. But the one for iron, which is rust, when you scrub it, it's able to fall down. And that's the main reason. So we say corrosion of aluminium leads to formation of aluminium oxide, which is resistant to water. It resists water. And corrosion of iron leads formation of hydrated iron 3 oxide, which comes out when scratched. Question number 7, part A. State and explain how the rate of reaction A gas plus B gas forming AB gas is affected by an increase in pressure. We know some of the factors that affect the rate of a reaction is pressure that affects mostly reaction that involves gases, and we also have temperature that also affects the rate of any reaction that is taking place. So in our case, we have A reacting with B to form AB, and in this case, they are all gases, and even the product is a gas. How does pressure affect the rate of the reaction? In this case, increase in pressure increases the rate of reaction. And by doing what? By bringing the reacting particles closer together, which results to more effective collisions. And when the collisions increases, the rate of reaction also increases. The rate or the number of effective collisions, once they increase, the rate of reaction also increases. That is a factor that affects the rate of a reaction. And this will only affect gases or molecules. Temperature. How does temperature affect this kind of a reaction? We know that temperature is known to increase the kinetic energy of the reacting particles. So once the kinetic energy of the reacting particles increases, also the effective collisions also increases, and that automatically increases the rate of the reaction. So we say increase in temperature increases the rate of reaction by increasing the kinetic energy of the reacting particles. And this leads to more increased number of effective collisions. So automatically, if the effective collisions increases, the rate of reaction also increases. Part B of this question, the rate of reaction between ethanoic acid and copper 2 carbonate can be monitored by measuring the volume of gas produced. The results obtained using 75.0 cubic centimeters of 0.1 molar ethanoic acid and excess copper 2 carbonate are shown in table 5. We can have a look at our table 5. In this case, our table 5 has two rows. We have time given in seconds, and we have the volume of the gas given in cubic centimeters. At 0 seconds, the volume of the gas was 0. At 5 seconds, the volume was 20. At 15 seconds, the volume moved to 41 cubic centimeters. At 25 seconds, the volume moved to 50. And at 5 seconds, the volume moved to 56. At 45 seconds, the volume moved to 59. At 55 seconds, the volume moved to 61 cubic centimeters. And at 70 seconds, the volume moved to 63. And at 80 seconds, the volume still remained at 63. So we notice something that between 0 to 70 seconds, there was a significant increase in the amount of the gas that was being collected. But after the 70th second, the amount of the volume of the collected gas remained the same. So we need to ask ourselves, why is it that the volume remained constant from the 70th second? So the first question, write an equation for the reaction that took place. In our case, we said that we are reacting a copper 2 carbonate and ethanoic acid. Ethanoic acid is an organic acid. We are reacting with a carbonate, and we know anytime we react an acid and a carbonate, we always obtain the salt, we obtain water, and we still obtain carbon dioxide and the gas that was being measured in our case here. So we have three products. So in this case, our reaction is going to be copper 2 carbonate plus 2 moles of ethanoic acid, and we obtain copper carbonate. We're going to obtain ethanoate, copper ethanoate, and in this copper 2 ethanoate, carbon dioxide. This is carbon dioxide, and water. Please not forgetting to include the state simples. Copper carbonate is a solid, ethanoic acid is aqueous, copper 2, we have copper ethanoate, in this case is aqueous. Then you have carbon dioxide is a gas, and water is a liquid. The equation should be balanced. So you balance by putting a 2 at the ethanoic acid, and you'll be able to score 1 mark. Give a reason why excess copper 2 carbonate was used. Why do we always use excess copper 2 carbonate? Anytime we have acid and a metal or a solid being reacted, we add the solid in excess to ensure that the acid being used, all of it reacts. So to ensure all the acid reacts. So in this case, the correct answer is to ensure that all acid reacts. So we have Roman 3 of question number 7. On the grid provided, draw a graph of results obtained. So in this case, you are going to have a graph of the gas produced against time. So in this case, we're going to choose the table or the values that you are given of the gas against time to draw a graph. In this case, we're going to choose an appropriate scale that is going to fit or to give us at least a graph that occupies a 3/4 of the space provided. So we start with the x-axis, where I label the axis as time in seconds. Then I have the y-axis, whereby I label it volume of carbon dioxide in cubic centimeters. Then I start putting the values of time. So I choose a scale. I choose 10 small squares to represent 10 seconds for the time. So we have 10, 0, 10, we have 20, we have 30, we have 40, we have 50, we have 60, we have 70, and we have 80. Then on the y-axis, I'll still use 10 small squares to represent 10 cubic centimeters. So we have 10, we have 20, we have 30, we have 40, we have 50, we have 60, we have 70, and we also have 80. So as you can see, I already have a sketch or the graph. So the graph is going to be a curve. It's going to be a curve, and you can see we have 3 marks for this for the curve, plotting, and half mark for labeling the axis in each case. So I already have the curve with me. So let's move to the questions. Use the graph to determine the rate of reaction at 10 seconds. So when you are told to use the graph that you already have drawn to determine the rate of a reaction, what you do, you come to your graph, then you look for that 10 seconds. So my 10 seconds is at this point. So at this point, I'm going to take a ruler and I draw a tangent that touches that point 10 seconds. Once I have a tangent, I'm going to look for 2 points. 2 points. So I'm going to have at the y-axis, I'm going to have a gradient whereby I'm going to look for a gradient which is going to give me 2 points for y-axis and 2 points for x-axis. So in this case, I'm going to have for the x-axis, I'm going to have, in my case, I'm going to take change in y over change in x to determine the rate. So change in y, in my case, it was 41 minus 20 over, for the x-axis, it was 15 minus 4. So when I did my calculations and subtraction, I was able to obtain 21 over 11, which gave me 1.9091 cubic centimeters per second, and that's the rate. Rate is given in amount of substance produced per given period of time. So cubic centimeters per second. You may also be in a position to obtain or to get a different value, which may not be very different from mine, but closer to it. But in this case, your answer is marked based on the graph that you already have. So everybody in this case is always correct, as long as you are within the range of the correct answer. So in this case, the value that I obtained was 1.9091 cubic centimeters, and you must have shown this working to show that you used your tangent and the gradient to obtain the changes in y and x. So this is how you were supposed to obtain the rate at 10 seconds. And Roman 2 of the same question, we determine the rate at 40 seconds. Again, when you move in the graph, you also locate 10 seconds and you move until you touch the graph or where the curve is, and you'll be able now to also have a tangent, and then you come up with 2 points on y and x axis, and from there you'll be able to determine the rate. So in my case, I was able to have for the change in y, 62 minus 50 over 53 minus 53 minus 18. So I'm going to, I have 12 over 35, and my rate was 0.34286 cubic centimeters per second. So again, we apply the same method that you had applied when you were determining the rate at 10 seconds, and we still obtain our rate in that case. Moving to the last question on this paper, give a reason for the difference between the two average rates calculated in Roman 4 above. So why is it that the rate at 10 seconds is higher than the rate at 40 seconds? So the difference is because the rate is higher at 10 seconds than at 40 seconds due to higher concentration of reactants at 10 seconds. So at earlier seconds or early stages of the reaction, the number of reactants or the amount of reactant is higher compared to the late moments of the reaction. And as we know, the concentration of the substance is another factor which affects the rate of a reaction, and automatically the rate at 10 seconds will be a bit higher than the rate at 40 seconds. So this marks the end of our presentation today. If you found the video useful to you, please subscribe to our YouTube channel, and as well like, comment, and share the video to reach as many learners as possible. Stay tuned, for we are going to bring more episodes of this kind. For the students who are preparing for the Kenya Certificate of Secondary Education, and even the continuing students, we are going to be dropping videos of this kind regularly. So kindly subscribe to our YouTube channel. We are going to be dropping videos on chemistry and even on biology. So kindly don't fail to subscribe to our YouTube channel. Feel free to comment your reactions, your suggestions, and give us your views concerning what we are supposed to drop in our next episodes. So thank you for watching. May God bless you.